The following presentation is on machine learning translation for the course ISM 6021, Management Information Technology. This is our agenda. First, we'll start with an overview and history of machine translation, followed by the timeline of development, relevant IT components, relevant costs, benefits, and risks, and finally, future trends. Machine translation is a branch of AI concerning the use of software to translate text from one language to another. Neural machine translation, or NMT, is a relatively new method that uses neural networks to perform machine translation. A neural network is a system that can be trained to recognize patterns in data, thereby transforming some input data into a desired output. Consider translating a sentence from French to English. In this context, the general process for NMT is as follows. You feed the input French sentence into the network, where each word of the sentence is represented by vectors of numbers so that the network can process it. Then the network performs many mathematical transformations on those numbers, ultimately producing a sequence of new numbers that represent the English output sentence. In practice, there is a four-step process for the system. First, before any translation can happen, the human engineers need to decide the architecture of the network. For example, how many and what type of mathematical transformations the network should apply. This requires significant expertise, a lot of experimentation, and a fair amount of guesswork. Once the network architecture has been decided, we have an untrained neural network. Second, the engineers then implement this network on computers with heavy processing power. Third, the network is then trained. A program is run to input millions of French and English sentence pairs into the network. With each sentence pair, the network first sees the French sentence, guesses what the English translation should be, and then is told how accurate its guess is relative to the provided correct English translation. Over many iterations, this training process enables the network to find the best settings associated with the mathematical transformations, and thus produce good English translations. Finally, the engineers test their NMT system by having it translate sentences that weren't used during training, to make sure it can generalize beyond the data it was tuned to work well on. During the Second World War, British computer scientist Alan Turing worked to crack the Enigma code, which was used by German forces to send messages securely. Alan Turing and his team created the bomb machine that was used to decipher Enigma's messages. This laid the foundations for machine learning. In 1956, American computer scientist John McCarthy organized the Dartmouth Conference, at which the term artificial intelligence was first adopted. Research centers popped up across the United States to explore the potential of AI. Researchers Alan Newell and Herbert Simon were instrumental in promoting AI as a field of computer science that could transform the world. Newell and Simon developed general problem solver algorithm to solve mathematical problems. In the 50s, John McCarthy, often known as the father of AI, developed the Lisp programming language, which became important in machine learning. In the 1960s, researchers emphasized developing algorithms to solve mathematical problems and geometrical theorems. In the late 1960s, computer scientists worked on machine vision learning and developing machine learning in robots. Waybot 1, the first intelligent humanoid robot, was built in Japan in 1972. From the mid-1970s to the mid-1990s, computer scientists dealt with a shortage of funding for AI research. These years became known as the AI winters. In the late 1990s, American corporations once again became interested in AI. The Japanese government unveiled plans to develop a fifth-generation computer to advance machine learning. In 1997, IBM's Deep Blue became the first computer to beat a reigning world chess champion, Garry Kasparov. Exponential gains in computer processing power and storage ability since the 1990s allowed companies to store and crunch vast quantities of data for the first time. In the past 15 years, Amazon, Google, Baidu, and others leveraged machine learning to their huge commercial advantage. Other than processing user data to understand consumer behavior, these companies have continued to work on computer vision, natural language processing, and a whole host of other AI applications. Machine learning is now embedded in many of the online services we use. Machine translation can be split into four periods of development: rule-based machine translation, or RBMT, example-based machine translation, or EBMT, statistical machine translation, or SMT, and neural machine translation, or NMT. The first ideas surrounding rule-based machine translation appeared in the 70s. The scientists peered over the interpreter's work, trying to compel the tremendously sluggish computers to repeat those actions. Prompt and systrand are the most famous examples of RBMT systems. RBMT has three subsets: direct, transfer-based, and interlingua. Direct machine translation is the most straightforward. It divides text into words, translates them, slightly corrects the morphology, and harmonizes syntax to return some kind of translation. Transfer-based machine translation determines the grammatical structure of the sentence first. Then it manipulates whole constructions, not words, afterwards. This helps to get a better conversion of the word order in translation. In interlingual machine translation, the source text is transformed to the intermediate representation and is unified for all the world's languages. Next, interlingua would convert to any target language. Because of the conversion, interlingual is often confused with transfer-based systems. The difference between the two is the linguistic rules specific to every single language and interlingua, and not the language pairs. A third language could be added to the interlingual system and translate between all three. In 1984, Makoto Nagao from Kyoto University came up with the idea of using ready-made phrases instead of repeated translation. EBMT, as it became known, demonstrated that machine can be fed with existing translations for comparative purposes instead of spending years forming rules and exceptions. In early 1990, at the IBM Research Center, a machine translation system was first shown which knew nothing about rules and linguistics. It analyzed similar texts in two languages and tried to understand the patterns. An identical sentence in two languages split into words, which were matched afterwards. This operation repeated about 500 million times to count, for example, how many times the word das Haus translated as house versus building versus construction, and so on. If most of the time the source word was translated as house, the machine used this. Note that no rules or dictionaries were used. All conclusions were done by machine, guided by stats and the logic that, if people translate that way, so will I. This was SMT. SMT has three subsets: word-based, syntax-based, and phrase-based. Word-based SMT worked by splitting the sentence into words, since this approach was straightforward and logical. In syntax-based SMT, it's necessary to do quite a precise syntax analysis of the sentence to determine the parts of the sentence, and then to build a sentence tree. Using it, the machine learns to convert syntactic units between languages and translates the rest by words or phrases. Phrase-based SMT is based on all the word-based translation principles: statistics, reordering, and lexical hacks. Although for the learning, it split the text not only into words but also phrases. Thus, the machine learned to translate steady combinations of words, which noticeably improved accuracy. NMT is the use of neural network models to learn a statistical model for machine translation. The key benefit to the approach is that a single system can be trained directly on source and target text, no longer requiring the pipeline of specialized systems used in statistical machine learning.
All right, timeline of development. So AI in the recent years has blown up and it's made strides and great advances, and it's starting to not just be the field of AI, but it's appearing in fields such as business and energy and manufacturing, and it's huge in the medical industry. Such things as the Apple Watch actually allows people that own an Apple Watch to detect heart arrhythmias. It's appeared in the culinary with the IBM Chef Watson. It's an AI that's creating its own recipes. Energy, BP is using AI to increase performance. Social media, all the platforms are using it to better connect to their users. And manufacturing, Volvo is using AI to better know when car parts will need replacing. Um, there's a little quote down to the left, but it kind of talks about all the things that AI is doing and what it is developing into and how it is making our industries more efficient. So experts are beginning to believe that AI won't replace jobs, but rather enhance work. Experts think that AI is replacing tasks, small tasks that people don't necessarily want to do, repetitive tasks, but not jobs. Some even actually say that it is creating jobs. There's now a need for people to manage these AI, create these AI, so coders, programmers, and technicians. And I mean, the AI industry is really taking off now, but it's expected to grow by 20% from 2015 to 2020, and it's just expected to keep taking off and keep incorporating itself into everyday life and everyday business. So relevant IT components. So types of models of AI include deep learning, machine learning, and neural networks. Deep learning are networks capable of learning unsupervised. Machine learning is AI can explore, learn, and improve on what they experience. And neural networks is a system based on the human brain. So, kind of how artificial intelligence is getting into different industries. Artificial intelligence taps into many areas of study to have a wider base of knowledge. So, computer science, engineering, ethics, logic, mathematics, philosophy, and then medical, culinary. I mean, you name it, it can learn it. So, hardware used in creating AI includes parallel processing parts, cloud data storage, and graphical processing units. Graphical processing units are most commonly used because they're good at parallel computing and have multiple cores that run simultaneously. It's kind of like neurons in a brain firing. There's a lot of things going on at once, especially with AI. So it needs something that can handle that. So companies are actually creating their own AI-specific software, such as Google's Tensor processing units, Microsoft's Field Programmable Gate Arrays, and IBM and startup companies like Wave Computing. Some programming frameworks for building AI include Python, TensorFlow, Java, to name. So AI applications include speech recognition, sentiment analysis, image recognition, navigation, virtual reality, genetic algorithms, and much more. Applications can vary depending on if the AI is a program or in the form of a computer or in the form of a robot system. If it is in the form of a robot, some parts can include but are not limited to motors, actuators, power supply, sensors, and muscle wires. AI robots are also being to be designed like humans, very lifelike, like the bottom left picture. So parts can also include to make it look human. Then parts of a computer system include, but are not limited to, a power supply, a processor, a software, and a display device.
Relevant costs, benefits, and risks. AI machine learning translation can be a major asset in the international trade scene, specifically for issues with language barriers. Estimates suggest that sharing a common language boosts trade among nations by about 50%. China has an average of 8 million college grads per year, many of whom do not speak any English. Machine learning translation gives them the opportunity to freelance their work even if they don't speak English. This movement has been labeled telemigration. Future of machine learning translation. AI translation has reached accuracy levels that are already equivalent to that of human translators. And with further machine learning, AI is set to surpass human levels in the next 2 to 3 years. For some people, this can be great news, and for others, this can be bad. Many experts predict that the 500,000 human translators and over 20,000 agencies will be unemployed in the near future as their jobs become more and more automated.
Although some experts, a big future trend. Language is subjective. In conclusion, we have walked through machine translation's overview and history.